Welcome back, everybody. Today's topics 1.14 connecting infinite limits and vertical asymptotes. As always, these are the notes for day 9. So today we're talking about infinite limits pretty much. So let's see the first two graphs that we have right there. We have f of x equals 1 over x minus 1. And then if you notice, it has a vertical asymptote. And g of x equals 1 over x minus 1 squared. And again, there is a discontinuity right there on the graph as well. So let's try to find these limits, find each limit, confirm the result with the graph above. So let's look at part A. The limit as x approaches 1 from the left side would be equal to, so coming in from the left side would be equal to what? So negative infinity. And if we're coming in from the right side, that takes us towards positive infinity. All right, and then part C, so therefore we can say again, these two don't match. So therefore the limit as x approaches 1 of f of x does not exist. Okay, and then let's look at the other one at g of x. So the limit as x approaches 1 from the left side, that takes us to positive infinity. And then coming in from the right side is also equal to positive infinity. Now, since both are still going in the same direction, right? Both of them are still going towards infinity. Just remember, even though it's going towards the same direction, the limit still doesn't exist, right? So therefore, does not exist. And then answer the question: What do limits that produce results of infinity or negative infinity say about the function? So pretty much, if you guys came to the conclusion that it is a vertical asymptote, right? So they have a vertical asymptote at those values. All right, asymptotes. And then let's look at example 2. So the definition of a vertical asymptote is when the limit as x approaches c from the left side of f of x is equal to positive infinity or negative infinity. And also the limit as x approaches c from the right side is equal to positive infinity or negative infinity as well. Therefore, our equation would be x equals c is the vertical asymptote. So in example 2, determine all the equations that represent vertical asymptotes for each of the given functions. So right here, pretty much what you want to do is find the limit. So let's just try to factor it, because we don't have to be finding the limit each time. We just have to make sure that like something happens, right? So let's factor the top. If you notice, x squared plus 1 can't be factored, so we're going to leave it like that. The denominator is a difference of 2 squares, so we can factor it into x plus 1 times x minus 1. So again, for sure, we know right here that the limit, right, if we approach 1 from either the left or the right side, we're going to be going towards infinity. So our first vertical asymptote is going to be equal to x equals positive 1 and then x equals negative 1. So let's do the same thing on the next one. So let's factor. So that's going to be x plus 4 times x minus 2. And then our denominator is a difference of 2 squares. So that would be x minus 2 times x plus 2. Now here, even though there is pretty much 2 discontinuities in the denominator, I want to make sure that the first one, x minus 2, if you notice, it divides out. So that is a removable discontinuity, right? It's a hole in the graph. So therefore, there's no asymptote. It's a hole right there. And then if you set that one right there, x plus 2, so that's the only one that's going to make that 0 is going to be if x equals negative 2. So our vertical asymptote is located at x equals negative 2. And again, if you notice by now, you've discovered that fairly simple rational functions finding the location of any vertical asymptote can be done without actually finding the value c. That x should be approached to ensure a limit that approaches either positive infinity or negative infinity. It is possible to find the asymptotes by reducing the rational function to its simplest form and then setting any denominator factors equal to 0, which is pretty much what we did right here in this example.